Next, let us take a look at global sensitivity analysis. In global sensitivity analysis, we will look for a measure for the sensitivity on a delimited area in the parameter space. So we will look at a very specific region in our parameter space and try to see how the parameter is behaving on this area. In order to perform a global sensitivity analysis, we need to know or choose the probability density functions for the different parameters. In this part, we will discuss 3 different techniques. We will take a look at standardized regression coefficients, screening techniques, and then finally variance decomposition. First off, standardized regression coefficients. These standardized regression coefficients are found using linear regression on a number of Monte Carlo simulations. So we have a model with p parameters, θ1 up to θp, and for all of these parameters we know the probability density function. Using these probability density functions, we can do a Monte Carlo simulation to obtain a set of parameter values. We then plug these values, θ1 to θp, into the model to get a simulated outcome y. And then we repeat this process n times, so we get n different set of parameter values and n different outcomes y1 up to yn. If we then do this not for just one time point, but for all the time points, we don't get n outcomes y1 to yn, but we get n functions y1 of t up to yn of t. And these n functions, they have been plotted in the graph you see on the slide. Each of the lines represents one of the Monte Carlo simulations for my outcome y. And the line indicated in blue then gives you all the different values, all the simulated values at time point t equal to 6. To determine the standardized regression coefficients, we then perform a linear regression at a certain time point. So for example, we will take the time equal to 6, t equal to 6, and do a linear regression on all the y values that we have at t equal to 6. The linear model then is y is equal to b0, the intercept, plus b1 times θ1, plus b2 times θ2, and so on up to bp times θp, plus some error term. At the chosen time point, we know θ1 up to θp, so we know the parameter values, and we have to determine b0, b1 up to bp, so we have to find the coefficients for this linear regression. We now have this equation n times because we have n simulations, so we have n outcomes y1 up to yn. We have n sets of parameter values, so there are n values for θ1, n values for θ2, and n values for θp. And so we can put this into a matrix notation as seen on the slide. So we get y, the vector y, an n-dimensional vector, is a matrix of parameter values, θ, times the vector with the coefficients b0 up to bp, plus a vector of error terms. We now want to estimate the values of the coefficients, so we want to estimate this vector, and we solve this through a least squares minimization problem. So basically you will minimize the error term, so you will take a look at the difference of y, your observed values, minus θ times b, your estimated values, and then you square this. Solving this minimization problem will give you values for the coefficients, and the ones we are interested in are b1 up to bp, so the coefficients which are associated with one of the parameters. So bi, the value that we have estimated, this will give you the respective contribution of the parameter θi in explaining the total variance of y. So the higher bi is, the more influence θi will have on my outcome y. One final remark with this slide. So we say we are doing a global sensitivity analysis, yet we are looking at a certain given time point. This is still a global analysis because we are not looking at a certain value of my parameters, but we are looking at a number of values, an entire range of values for my parameters. So it is not a local analysis. For a local analysis, we look at one time point and only one set of values for θ1 and to θp. Here it is global, we look at one time point, but we have a different number of parameter values for θ1 and θp. To make sure that we can compare the different calculated coefficients, we have to standardize them. So we have to correct them for the spread, both on the parameter and on the output. We thus take the value for the coefficient, bi, we multiply with the standard deviation on my parameter, sigma theta I, and then we divide by the standard deviation for the output, sigma y. So basically, we multiply the calculated coefficient bi with the proportion of the total variance explained by the variation in theta I. These new standardized coefficients are what we call the standardized regression coefficients, or SRC, for theta I. We can very easily calculate the standard deviations because we did a Monte Carlo simulation. For y, we just take the vector for the output, y, so y1 up to yn. We calculate the standard deviation on this vector. And then for the different parameters, we look in the matrix theta. The second column there gives me theta 11 up to theta n1, so these are n values for theta 1. Here we can calculate the standard deviation for the first parameter. The third column contains n values for theta 2, so we can use these to calculate the standard deviation for the second variable theta 2, and then the last column will be used to find the standard deviation for theta p. If the parameters really follow a linear model, then it can be shown that the total variance will be explained by the SRCs. It can then be shown that the sum of all the squares of the SRCs is equal to 1. If the parameters actually follow a non-linear model, then our linear regression is only an approximation, and we will not explain all the variance. The part that is explained is again given by the determination coefficient, just the same as in a regression analysis, r squared. And then we will say that our technique is usable, it is valid, if r squared is at least 70%. So the model must be linear enough, sufficiently linear, to be able to use standardized regression coefficients. To recapitulate, first you get n values for the outcome y using Monte Carlo simulations. Then you fit a linear regression model based on your Monte Carlo simulations. And then you calculate the SRCs, the standardized regression coefficients, as a direct measure of the sensitivity. The goal of screening techniques is to obtain an idea of the importance of the different model parameters using only a very limited number of simulations. For screening, we thus use a limited number of simulations instead of a lot of simulations that we used for Monte Carlo simulation. And as such, we have a relatively low computational cost compared to the other methods. The main idea of these screening techniques is to quickly identify which parameters or which inputs are important or have a significant contribution to the output, and not really to quantify exactly the sensitivity. So screening techniques are good as an initial approach, a preliminary analysis, to weed out or to get rid of the parameters with very little influence before we apply a more detailed technique. Most of the popular screening techniques will make use of the elementary effect. Recall that we have p parameters, theta 1 up to theta p. The elementary effect for parameter theta I is defined as y evaluated in theta I plus delta minus y evaluated in theta divided by delta. For y evaluated in theta, we just take the values for theta 1 up to theta p. Y theta I plus delta, we keep all those values the same, except for the value of theta I, where we add a perturbation, a predetermined step size, to this value. So y of theta uses theta 1 up to theta p. Y of theta I plus delta uses all the same parameters, theta 1 up to theta p, except for theta I, which we change. So the formula is quite analogous to a local sensitivity formula. However, the step size is a lot larger, so it is not really a local formula. How does this screening then work? Assume we have two parameters, theta 1 and theta 2. This is the easiest to illustrate. What we do is we choose locations in the parameter space in a very systematical way. We start by looking at the parameter theta 1, and then we make sure that we cover the entire range of theta 1. So we make sure that we cover all the possible outcomes of theta 1, and this for all possible options of theta2. The screening method will provide us with two sensitivity measures for each input, namely a mean and a standard deviation. The way that we obtain these sensitivity measures is through a design based on the construction of a series of trajectories in the input space. Each of the parameters is assumed to vary across k selected levels in the input space, where k is determined by the step size delta. For each of the trajectories, we then calculate an elementary effect. In our example, the striped lines indicate the delimited area, so the possible values for theta1 and theta2. And we see that for the parameter theta1, the trajectories have been chosen in such a way that every possible value that corresponds to one of the k levels has been used as an input as a start point for a trajectory. Furthermore, we have chosen the trajectories in such a way that each of those corresponds to a different level of theta2, so we cover all the different levels of theta2 as well. In our example, we have 4 of those steps from theta1 to theta1 plus delta. This gives us 4 elementary effects for the first parameter theta1. And with this vector of elementary effects, we can calculate the mean for the elementary effect of theta1 and also the variance or the standard deviation for this elementary effect. So we obtain two sensitivity measures for each parameter, the mean of the elementary effect and the standard deviation of the elementary effect. The mean will indicate the average effect that this parameter has over the entire parameter space. And so the larger the mean, the more important the parameter. The standard deviation gives us information about the linear behavior of the parameter. If the value is large, this means that the parameter has a nonlinear behavior, or there would be interactions between this parameter and other parameters. It is important to analyze or look at both of those measures simultaneously. So you have to look at them together, and then you can distinguish 3 groups. Either there is a non-significant effect, so mu is very small, or there is a large linear effect, mu is large but sigma is small, or a large nonlinear effect when both of the values are large. And then you do identically the same for the parameter theta2. This will then enable you to compare the effect of changes delta for the different parameters. The graph of the left gives us the final result of trajectories for the initial screening method. So we have taken steps in theta1, so we have 4 trajectories in theta1, and then we do the same for theta2, which will also give us 4 trajectories. Each of those trajectories will correspond to an elementary effect, and for each elementary effect we need to make 2 simulations, one for the starting point and one for the end point. For the example, you see that we will need 16 simulations. How would we obtain this in a more general way? So 16, we see we have 2 parameters. For each of the parameters we have 4 elementary effects, and for each of the elementary effects we have 2 simulations. So the general formula for the number of simulations is the number of parameters p times the number of elementary effects, which corresponds to the number of levels k, times 2 simulations. In 1991, Morris introduced a more efficient way to obtain the same screening. This Morris screening, this will take each endpoint of theta1 as a starting point for a trajectory in theta2. So here now, instead of 4 points, 4 simulations for 2 elementary effects, we only need 3 simulations for 2 elementary effects. In the example, the 16 simulations are now reduced to 12 simulations. This value of 12 is obtained as being 3 simulations per set of 2 elementary effects times the number of elementary effects per parameter. In general, this is 3 simulations for 2 elementary effects. This will correspond to p plus 1, the number of parameters plus 1, times the number of levels that we have defined. In our very simple example, we see that there is a reduction from 16 to 12, so already 25% less simulations, and the effect becomes more important if the dimension or the number of parameters increases. And then the third method that we will describe is variance decomposition. Here what we will do is we will split the total variance in the output in parts which are related to the different parameters. So we will try to find the share of each model parameter in the total variance of the model output. Since the previous methods all are some sort of a linear approximation, this variance decomposition method, this is mostly used if the model is strongly non-linear or if it is non-monotonous, so there are a lot of ups and downs in the model. If we take, for example, a model with 3 parameters, then we know that the total variance is the variance of the first parameter plus the variance of the second plus the variance of the third one, and then all the covariances or the interactions between the different parameters. It is exactly this decomposition of the variance which will allow us to take interactions or nonlinear responses into account. Next, we divide this formula by the variance of y, so basically we will normalize this to obtain the sensitivity indices. Since 1 is equal to 100%, this means that the sensitivity indices will indicate which fraction of the total variance is determined by a certain parameter or a certain parameter combination. If we then want to determine, for example, the influence or the total influence of the first parameter, we can calculate the total sensitivity index for the first parameter. So ST1, this will be the sum of all the sensitivity indices in which parameter 1 plays a role. So it is S1, S12, S13 and S123. Similarly, ST2 will be the total sensitivity index for parameter theta2 and ST3 the total sensitivity index for parameter theta3. Each of those gives us the contribution of the parameter, including all the interaction effects. Of course, the sum of ST1, ST2 and ST3 will be larger than 1, will be larger than 100%, because the interaction effects are now counted multiple times. So we see S12 appears in ST1 and in ST2. S123 appears in all 3 sensitivity indices. To find such a decomposition, to find such a variance decomposition, there are 2 popular techniques: FAST, Fourier amplitude sensitivity test, and Sobol indices. You don't have to know the details, you just have to be able to apply those in R. The first technique, FAST, is based on the Fourier decomposition of the model output. It is possible to determine the first order effects with this, and with an extension, extended FAST, even the total effects. But FAST is very computationally intensive. Sobol indices, on the other hand, will use multiple integrals instead of Fourier decompositions, and they can be used for first order, but also for higher order effects. The drawback, of course, is that if we include those higher order effects, this becomes computationally very explosive, and the technique is less efficient than FAST.